Welcome back from spring break. Hopefully, everybody had a nice, refreshing time off. Um, anyways, some information here. So, everybody should have taken the midterm exam, okay? And I think there were only a few of you that I noticed that had a couple questions that required specific grading on my part, but I took care of those as early as I could. So, everybody should have your grades. Um, you know, as is pretty typical, grades were across the board. So I will admit I am uh, very happy to say there were a couple of people that actually aced the exam. So good job on that. All right. So yeah, and then there's also a couple of you who have not taken the midterm. Okay, so it's late. Get it taken. I don't know what else to say. Okay, you get points are getting deducted day by day, so get it taken. Otherwise, you'll find yourself with a super bad grade. Okay. All right. Well, let's go ahead and transition on to today's topic, which is physical oceanography. Let's see. I'm gonna go ahead and switch over here to this presentation. I guess before we get started, are there any questions on anything? All right, hearing nothing, we'll go ahead and get started here. So, so chapter 15, this is also kind of at least what I think is kind of a fun chapter. It's really informative. It's interesting stuff, though some of you may disagree with me, but I think it is it's pretty fun stuff to learn. So as usual, if you have any questions during the lecture, feel free to just go ahead and come off mute and ask away. No need to hold off until the end of class or anything like that. All right. So we're going to be looking at the physics of oceanography. Don't be scared because this is quite fun stuff, actually. So we're going to basically be looking at movement of water. Okay, so first and foremost, what I want to differentiate here between here is ocean currents and waves. Okay, everybody knows what a wave is, and the technical definition of a wave is basically it's that interface between the atmosphere and the ocean water itself. Okay, and waves are caused by friction from wind blowing across that interface. Okay, so that's kind of the technical definition there, or way to describe it. Ocean currents are very similar but different from waves. Okay, they're not the same thing. The ocean water, or ocean currents rather, are a lot like waves. They're still moving water around. Okay, but ocean currents move water around in a different way. Okay, and actually, I'll get to that. I'll get to the explanation here in a couple slides, and including the difference. Let's see. So in this picture here, what you're seeing are major ocean currents on Earth, okay, in the Earth's oceans. Okay, the red lines represent warm ocean currents, cold lines represent, or the blue lines represent cold ocean currents. Okay, and the arrows point in the direction of the current movement. And what I want to point out here is a couple things. Okay, first is the warm ocean currents. They originate at or near the equatorial regions, and their job is to transport warm equatorial water toward the polar regions. Okay, so you'll notice that the red warm currents, you'll see them, some head upwards in the picture, some will head south or downward in the picture, going toward the two different poles. Okay, the cold currents, or the blue ones, are the exact opposite. They originate in the cold polar regions, and their job is to take cold water at the polar regions and move that coldness toward the equatorial regions. Okay, so really what you're seeing here with ocean currents is just merely, you know, waters of different temperatures being moved around Earth in order to reach kind of an equilibrium. Okay, as you'll see, well, as you have seen and will continue to see throughout Earth science, is that Earth is a very dynamic system, yet somewhat predictable. Okay, by that I mean there are Earth is always trying to reach some sort of equilibrium. Okay, whether it's erosion versus uplift, um, or with transport of air in the atmosphere, or transport of water in the oceans. There's is always trying to maintain an equilibrium, like I said, by moving the hot or the warm and the cold currents from one place to another, basically. Okay. So currents, a lot like waves, do move partly as a result of friction. So you have one water molecule in direct contact with its neighbors, and of course, if that one water molecule is moving, that means that there's friction between it and its neighbors. Okay, so you're gonna see all of them starting to move. Okay, so a little bit. Let me see here. So I think I already covered this. Yeah, so I covered this. The main thing to get out of this chart here is that the warm current is warm and the cold current is cold. Okay, but really, if you look at the difference in temperature, it's not substantial, but it's enough to make a difference. Okay, so if we look here at cold current versus the warm current, okay, um, it's it's bordering on about a 10-degree Fahrenheit difference. Okay, and that's actually quite a bit for water. It takes a lot of energy to heat up and cool down water. Okay, this is also another setup that's pretty common where we see a cold current on the west coast of continents, a warm current on the east coast of continents. Okay, that's true of North America as well. So, contrary to what you may think about the sunny, warm waters of Southern California, that is actually a cold current, the California current. Okay? It's actually water coming down from the Alaska region headed south toward the equator. Okay, so if you want warmer water to swim in the oceans, head down to the Gulf of Mexico or the Atlantic. Okay, all right. So, okay. Okay, now in the oceans, there are 5 major um, features called gyres. Okay, a gyre, you're going to see this same concept come up again when we talk about meteorology as it applies to air. But in terms of oceanography, gyres are basically slow-moving circular paths of water. Okay, so we have ocean circulation that's occurring in big, huge circles. Okay, and I know it may not be completely evident, but here's a good example in the Atlantic, the North Atlantic. This is a gyre, okay, one of those huge gyres. So water essentially, the ocean currents move in a clockwise direction via these 4 different ocean currents. Okay, so there's a handful of them in other places. So right here in the South Atlantic, North and South Pacific, and then there's one in the Indian Ocean as well. Okay, so currents, or rather deep ocean circulation, I should say, um, how it moves um, is by temperature, density, and salinity differences. Okay, so let me kind of explain that. So we know that temperature-wise, warm things rise, cold things sink. Okay, Uh, in terms of density, we know that lighter things will float while heavier, aka denser things, will sink. And then salinity is essentially driven. Well, salinity, the amount of salinity rather, also determines density. Okay, so basically, when we put these three factors together, when we have high salinity, okay, that's always going to be associated with dense cold water. Okay, so high salinity, dense cold water. Low salinity is always going to be associated with less dense, warmer water. Okay, so as you can see, basically what I'm saying is temperature, density, and salinity. Those are all interrelated, but really it's differences in those factors, in those variables rather, that um, cause the movement of ocean circulation. Okay, so let me kind of explain how this works. There's this thing called thermohaline circulation. It's also known sometimes as deep ocean circulation. Okay, that's this picture you're seeing here. Basically, this is pretty much what I just explained, where you have warm water originating at the equatorial regions. Um, that warm water, again, is lightweight, so has low density and it has low salinity. Okay, it stays that way as it moves its way around kind of the equatorial regions. Okay, but notice that when the deep ocean or when the thermohaline circulation starts to move down here toward the South Pole, notice that it sinks. Okay, so the current itself finds itself going from higher up in the ocean to down at the bottom. Okay. And the reason why that happens is because as it moves south, the water cools down. Okay, as a result of cooling down, it becomes denser. Okay, and it becomes more saline. Okay, so that's why you're seeing this kind of bluish color down here, down by where Antarctica is. Okay. But this thermohaline circulation is often described as a global conveyor belt for currents, for ocean currents. It is essentially the path in which ocean circulation occurs worldwide. Okay. Water moves in this specific pattern. Okay, so that's deep ocean circulation. Okay. Now, kind of going back to waves again, I said earlier that waves are essentially caused by friction from wind that's blowing along the interface between the atmosphere and the ocean. Okay, so right at the top of the ocean where the water meets the air, okay, you have that friction between the wind and the water. Okay, now again, the difference between waves and circulation is that the waves are driven by that friction from wind, whereas with circulation, that circulation is driven primarily, mostly by the density, temperature, and salinity differences that we just looked at. And so two different ways for ocean waters to move. Um, Circulation, also keep in mind that circulation refers to below the surface. Typically, waves are going to be right at the surface of the ocean as well. Okay. Before we move on to talk about the anatomy of a wave, are there any questions about currents or circulation? Okay. All right. All right. Well, let's talk about waves then. Okay. So just mainly terminology here for this first part. Okay. So parts of a wave. Okay. The crest is the highest part of the wave. Okay. The peak. The trough is the lowest part here. The wave height is the distance between the crest and the trough. Okay. So that's a numerical measurement. A wavelength is the distance between two two successive crests, so two different waves. The wavelength is the measurement of distance between one crest and the next crest, or one trough and the next trough, basically. Okay. Then you have wave period. Okay, wave period is a lot like, let's say you're standing on a pier with waves coming in. Okay, you're sitting there with your stopwatch, and what you're trying to do is measure how long does it take for one complete wave so to pass by you. Okay, because you're a stationary object. So what you're doing is you'll start the clock when a crest, when one of the crests goes by you. Then you'll stop the watch when the next crest goes by you. Okay, and the time that it took for that one wave to go by is your wave period. Okay, so time interval for one wave pass a fixed position. Okay. Before I get into this, let me kind of elaborate a little bit on this diagram down here. Okay, so what we just looked at, the typical physical terms associated with a wave, but what you might not be familiar with is these circles here. Okay, so these circles represent movement of essentially individual water molecules. Okay, because when you look at oceanography, or the movement of ocean water, you really need to kind of think of it at a micro level. You have to think, how is the water moving? Water molecule by water molecule. So how is the water moving in relation to the molecules that surround any given molecule, basically? Okay, so so what you see here is this line down here, this dotted line that says negligible water movement below 1/2 wavelength. Okay, that's called wave base. Okay, and I can go ahead and on the next slide here. So the wave base, which just happens to equate to 1/2 of the wavelength, basically is a point where the movement of water becomes negligible. Okay, that means either pretty minor or not existent at all. So that means that if you were to dive down into open water, open ocean, if you were to dive down below 1/2 wavelength or the wave base, you would be surrounded by calm water, no matter how rough the seas are. Okay, so that's kind of an interesting thing that happens there. But you might be asking, why does that happen? Because basically the effect of friction on the water as a result of the waves, it decreases as you go down. Okay, so there's more friction up here at the top. There's less friction as you go down because the water molecules at the bottom aren't moving nearly as fast. Okay, so that's kind of what these big circles represent, is faster, bigger movement, essentially. Yeah, so I'm going to come back to this slide and explain the rest of it here in a minute. So actually, I think I may have explained it all already. So water particle motion. Yeah, actually, yeah, I think I did pretty much explain that. Okay, so then let's talk about, how water moves as you go from open water on toward the beach environment. Okay, so notice here the wave base is out in open water. Okay, but then right here, wave base finds itself touching the sandy bottom of the beach. Okay, that's a very interesting spot. Okay, and that has very profound impacts when that occurs. Okay, so waves that are out in the open ocean tend to have a very long wavelength. Okay, and relatively low wave height. Okay, Now, once the wave base touches ground at the beach, then what starts happening to that wave is that its height starts increasing and its wavelength starts decreasing. Okay, so by that I mean because of the friction that's now occurring at the bottom of the beach, what's happening is the water at the bottom is slowing down. And so basically you have a wave that's getting squashed together. So it's, yeah, so its wavelength is decreasing, and concurrently its wave height is increasing. So wavelength decreasing, wave height increasing. There we go. Yeah. And the main reason why that happens is because basically what you're getting is you're getting the same amount of water squished into a smaller space. Notice how as you keep going up the beach, the waves keep growing upward in height. Okay, that's because the further that the waves advance toward the beach, okay, the less space that they have. So naturally the water or the waves are going to increase their height and decrease their wave height. Okay. So that's one thing that happens. Another thing is associated with friction. Okay, so notice how the movement that you see in these blue circles is straight up and down when you're out in open water. Once you reach wave base at the beach, where the wave base starts touching solid ground, you get a lot of friction that develops between the water that's in direct contact with that sandy beach, sandy bottom. Okay, so what starts to happen is that starts to slow down the water that's in direct contact with the bottom of the beach, while the water that's not in direct contact, so all the water above it, keeps going pretty much at its same speed. So the end result is you start to see this uh, leaning forward type situation with the wave. You notice how the circles are all kind of leaning forward a little bit. Okay, that will continue to occur as the waves get closer and closer to the beach, okay, to where they what's called break, where they break. Um, Eventually, these waves they'll start to lean so much that gravity will take over. And gravity, as you know, has a tendency to pull things straight down. So when these lean forward too much, the top of the wave will topple over the bottom part, and that's what results in the surf or the breaker rather. You've probably seen pictures of waves from like Southern California where they have that nice curl at the very top, and then it looks like they're leaning forward. Okay, perfect example of this. So they're leaning forward, and that top has that curl on it. Okay, it's that top part that eventually gravity takes a hold of, and it comes crashing down. Okay, so that's when the wave breaks. Okay, so I think that's about all I can really explain about what happens in the beach environment. Um, are there any questions about waves or what happens to waves when they come in closer to the beach? Okay. Well, I will say this. Okay, part of your assignment is to watch, was rather, to watch Earth Revealed video number 24. Okay. If you did not watch that video before class, I strongly encourage you to do so after class because they actually show you this very concept in an actual water tank, okay? And it's really quite interesting. All right, so hearing nothing, let me see if there's anything. Okay. Hearing nothing, we'll go ahead and continue on. So now we're going to look at erosion and deposition in the beach environment. Okay, so There's really two different ways that erosion occurs in the beach environment, and that's through just wave impact, so just by blunt force from water literally crashing into solid rock. And then there's abrasion. Okay, abrasion is kind of a sawing and grinding action. You might remember that specific action when we talked about glaciers, because glaciers abrade. Same concept where you got, but in this case, you've got that's water that's armed with a lot of sand, all sorts of debris, basically. Okay, the waves will smash up against these big rock faces on the shoreline. Those are called headlands. We'll talk about them here in a minute. So the waves will smash up against these headlands, and basically, in addition to just battering them and causing mechanical weathering, the material in the water, physically mixed in with the water and the sand, is also abrading. It's actually acting like a sandpaper. So it's kind of sanding away at the rocky outcrops as well. Okay, so those are two very common ways that erosion occurs in the beach environment. Okay, now the material that makes up a local beach is really pretty much heavily dependent on what kind of material is locally present. Okay. Most of us, myself included, probably think of a beach as nice sandy beach, right? Kind of that tannish colored sand. And that is true for a lot of places. That kind of sand is what results from the breakdown of pretty much any silica-rich rocks. Okay, a lot of times granite, and there's a lot of granite on the continent, so it's not surprising that the quartz constituency, which is what sand is essentially quartz, very finely broken up quartz. So it's not surprising that because there's a lot of granite, that beaches on continents have a lot of tan-colored sand. Okay, but in addition to that, beaches, like I said, are just the materials are made up of whatever's locally available. If you go further up into the Pacific Northwest, you'll see beaches that look like this, where there's cobbles. Okay, just beaches of cobbles, not very fun to lay down on with your beach blanket. Okay, I can attest that one. But that's because of the the specific local situation. We have a very tectonically active area where there hasn't been a lot of time for erosion to occur for a lot of these materials. Okay, plus they're very durable igneous rocks. But more specifically, I'll point you guys to, let's talk about Hawaii, for instance. I'm sure you've heard of black sand beaches, green sand beaches. Maybe you've heard of those. So basically, black and green sand beaches, those are just broken down mafic rock. So basically broken down basalt. Okay, so you have pyroxene, that's the black mineral. That will break down into black sand. And then olivine, which is often a yellowish to greenish colored mineral, will break down into greenish to yellowish colored sand. Okay, so anytime you see beaches with different colored sand, or if they look like this, just know that's material that's locally available. Okay, so that's what makes Mother Nature really interesting, is how Mother Nature makes different beaches with material that's at hand. Okay. All right, so that's a look at the material itself. Now let's talk about refraction here. So I had mentioned these rocky outcrops. These are very common on the West Coast, not on the East Coast or the Gulf Coast. And I'll talk about that a little bit later, explain why. But for now, just know that on the west coast of the U.S., we have a lot of these rocky outcrops called headlands. Okay, and what's happening is you have water, waves coming in from the open ocean. Okay, their direction is shown by these red arrows, and the topography at the bottom of the ocean here, or the bottom of the beach, I should say, rather, it varies. It's never the same anywhere, and so how waves come in to a beach is all dependent on what the topography of the beach bottom is. Okay, but there is one thing that does tend to happen no matter what the topography is, and that is wave refraction. For some reason, waves when they tend to come in towards headlands, because of the way erosion has occurred in front of the headland itself, the waves will often refract directly towards those headlands. And then they'll attack those headlands straight on, okay, which is what you're seeing with these red arrows. You can see the refraction here. They're basically turning to the left here, turning to the right here, okay? And they just smash right at that headland, okay? That's how Mother Nature gets rid of those headlands. You see, Mother Nature does not like headlands. Mother Nature likes very smooth coastlines. Okay, and a headland is a pain, So Mother Nature wants to get rid of that headland so that there can be that smooth, very long, gentle coastline. Now, in addition to refraction, is something called longshore current. Longshore current is just generally described as the direction that waves are moving in relation to the shore. And so, as a general rule, longshore current is going to be in the direction that the wind is blowing. Okay, so in our area, in our latitude region, winds are called the westerlies because in our latitude region, winds tend to move from west to east. Okay, not all the time, but the majority of the time, winds move west and east, as do storms, all weather. Okay. But anyways, I'm kind of getting off topic here. With longshore current, so in our area, generally longshore current is going to be in some sort of westerly, easterly direction because of the westerlies. But what you're seeing here in this picture is the longshore current. You see that the wind is blowing the water at an angle that's different than coming directly onto shore. Okay, and basically that has an effect with sedimentation of sand at the beaches. Okay, and this concept is called longshore transport. So basically, what you have is two different actions occurring simultaneously, well, one after another. And those are reflected by these two green arrows. You got the darker arrow here, and then you've got this kind of lighter green looking arrow. Okay, so this is how longshore transport works. Okay, so first is the dark green arrow. We can see that the longshore current is bringing in the water, which also is, holding a lot of sediments as well. It's bringing that water in at a 45-degree angle maybe onto shore. So it'll roll up on shore at a 45-degree angle here. And then because of the effects of gravity, okay, that water won't roll back down at 45-degree angle. No, it will roll back down the face of the beach straight, which is this kind of lighter colored green one. So that, where the water rolls straight back down into the water, that is due to gravity. Okay, so just remember that gravity is the reason why that happens. But either way, what this results in is the movement of sediment, like sand mainly, in a down beach environment. Okay, hence the term beach drift here. Okay, So because you get water that comes in at an angle and then it washes straight back down, the next wave comes in, washes in at an angle, comes straight back down, and you can see that creates a zigzag pattern that basically very slowly transports sand down beach in the direction of the longshore current. Okay, so having said that, if you go to a beach this summer, the sand that's there will not be the same sand that is there the next year. Okay, because what's going to happen is the sand that was there is going to move with the longshore current downwind. Stuff that's upwind, so sand at another beach that's upwind, is going to bring that sediment down to your beach over the course of that year. Okay, so it's kind of like a very continuous cycle of recycling sand based on movement of sediment by the longshore current. So really pretty interesting, pretty interesting concept here. Next time you're at the beach, just stop and take a look at how the water's coming in. And, if you really want to make it fun, go into the swash zone. That's that area where you can just wade into it. It comes up to like your ankles. Okay. Watch sediments. Watch how they're moving as each wave comes in and goes out. You'll see that the sediments, if you can keep track of, a certain sediment, which is hard, you'll see that they will be moving in the direction of longshore current. So it's actually really kind of cool to see in person. All right. So are there any questions about water movement or longshore current before I move on to other erosional features? All right. All right. So some other erosional features. Okay. These two features are associated with what's called um, they're tectonically active beach environments, basically. So this is what you would find on the west coast of the U.S. present day. So first you have a wave cut platform. Okay, we know that in this scenario, because the area is tectonically active, this kind of wave cut, flat looking area has been uplifted by tectonic activity. It was once below the water level, but it's been lifted up. Likewise, this marine terrace is just an old wave cut platform that's been lifted even further up. Okay, so this area here, notice how it's also very flat, just like this wave cut platform. Okay, they just represent different sequences of uplift. Okay, that's all it is. And this is the environment in which headlands often form. Okay, marine terraces are often the source of headlands, at least on the west coast. Okay, two other erosional features that are associated with headlands, typically. You see arch, okay, that's pretty self-explanatory. You get weakness that basically results in erosion in this circle part of the arch, okay? And that could be for many reasons. Could be just, weak cementing of sedimentary rocks. It could be the presence of cracks, joints, whatever. There's a host of reasons why, this area would erode while this other area, the rest of the arch, doesn't. But basically, a C arch, of course, has that arched feature with the hole in the middle that's eroded. A C stack is just a collapsed C arch. So if you can see that this chunk over here, this is the other side of the arch, the former arch. So this was once an arch right here. You can see the cursor. So that just means that the top of the arch collapsed, resulting in two just kind of big chunks of rock standing next to each other. Okay, those are called C stacks, just those big solitary all chunks of. Okay. If you go up to the Oregon and Washington coast, you'll see a lot of those. Very, really cool beach environments out there. So I highly recommend it if you ever get a chance to go out there. All right, so now we're gonna kind of transition away from the typical features of what you're gonna see on the West Coast to depositional features, which tend to be more of what occurs on the East Coast. Okay, you still get depositional features on the West Coast, but because it's tectonically active, a lot of what's happening on the West Coast is erosion. Okay, but if we turn our attention to the East Coast and the Gulf Coast, what you'll see is a lot of these depositional features. Okay, so first we'll start with a spit. This is basically a ridge of sand that extends out from a land area into kind of like a little bay area. And at the very end of the spit is going to be kind of what looks like a hook that's hooking inward toward the bay. Okay, and that's right here. You can see that hook. Okay, that hook forms because of the way that water slows down as it comes into that bay. Okay, so as water slows down, the water is actually naturally making kind of a hooked movement as well. And as it's slowing down as it gets into that bay area, it's depositing sand in that hooked kind of appearance. Okay, so that's how a spit forms. A baymouth bar. Okay, these often take on appearance very similar to another feature called a barrier island that we'll look at next. But basically, a baymouth bar is just a big, long sandbar that crosses a bay. And so the end result is that you have open ocean on one side, which is this side here. So this right here is the baymouth bar. Open ocean over here, and then on the landward side, you actually have what's called like a lagoon or a backwater lagoon. They also call it a tidal delta. That's perfectly fine too. So you'll have that lagoon form in between the baymouth bar, and this is the mainland area. Okay, so that's a baymouth bar, just basically a big sandbar. Okay, and lastly on this page is the tombolo. Okay, this is a basically like a narrow ridge of sand, which you can see right here, that connects this mainland area to this sea stack. Okay, that's pretty much all it is. So a sea stack that's connected to land by a very narrow ridge of sand. Okay, and then lastly, our barrier islands. So barrier islands, as you can see, they are a lot like baymouth bars. I'm not entirely sure why they differentiate between them, quite frankly, but barrier islands do tend to be bigger in size, and that may be why. So it's not entirely well understood why barrier islands form, okay, because from a physics viewpoint, it doesn't seem logical, okay, but it most likely has to do with the topography, the local topography. Did we get a question? Let me see here. Spit looks like a baymouth bar, but smaller. Yeah, exactly. The spit, not the spit. I'm sorry. Um, um, where am I blanking at this one? Barrier Island. Sometimes you'll get a break in between, like the Barrier Island. There'll be a break where um, basically water can transit between the lagoon and the open ocean here. That's called a delta. Yeah, it's pretty common. So let's see, what was I getting at here? So barrier islands, well, regardless of how they form, they're actually quite useful for Mother Nature. Okay, because they, number one is they take a lot of the brunt of force from hurricanes. Okay, barrier islands are very common on the East Coast and the Gulf Coast. Okay, you won't ever find these on the West Coast, but in the Gulf Coast specifically, yeah, they take the brunt of the beating from hurricanes, and which ultimately protects the mainland area quite a bit. And so that's good. Um, but like I said, they take a lot of beating, and there are some developments on barrier islands, actually quite a few, and that's not a good place to live. I'll tell you that. Those places are kind of a death trap during hurricane. So yeah, definitely stay away from them during hurricanes. They are really cool to see when there's no hurricanes. Definitely worth going out to check out and take a swim in the ocean while you're at it. All right. So now we're going to talk about the two different types of coastlines. I mean, essentially, we've been talking about these. These are just really just putting additional terminology to what we've been talking about. So um, when I was mentioning, the West Coast, where you have, headlands, cliffs, terraces, wave-cut platforms, sea stacks. That's just 100% typical of the West Coast. And that type of coastline is just generally referred to as an emergent coastline. Okay, they call it emergent because the land essentially is emerging from upward from the water, and that's because of tectonic activity. Okay, and then the East Coast and the Gulf of Mexico are just generally where a lot of the positional features occur. Um, this is called submergent coastline. It's because the generally, as a rule of thumb, because of the increase in sea level due to climate change, sea levels rising and it's submerging existing land. Okay, so it's basically flooding. Sea levels rising and it's flooding onto land areas. Okay, so I think I covered all this. So yeah, this is very typical of California coast right here. Very hard to get down to the beaches unless, Southern California is a little different, but pretty much the rest of California is super difficult. All right, so yeah, with submergent coastlines, the basic thing is that yeah, either sea levels rising, which is resulting in flooding of the land, or the land is sinking. Could really be either or, but as a general rule, because of the effects of sea level rise for climate change, it's generally from sea level rising. Okay, these are um, observable as having irregular shorelines. Okay, and that's because these are essentially this thing like the Chesapeake Bay here and the Delaware Bay here. Those are actually rivers. Okay, they're rivers that have been quote drowned. Basically, rivers that have been river valleys that have been flooded by the sea level rise. Okay, and the technical term for these drowned rivers is called an estuary. Okay, so that is to say, like the Chesapeake Bay, Delaware Bay, as sea level rise continues, they're going to flood more and more air, so they're only going to be getting bigger in size. All right. Any questions before I move on to tides? Okay. Not hearing anything. I will continue on. So tides. Okay. As you're probably aware, tides are that daily change in the elevation of the ocean surface, so AKA the sea level, based on the pull of the moon. Okay, the gravitational pull of the moon. So the moon itself naturally exerts a pull on water on Earth. Okay, and so that means that all water on Earth, okay, even the water in your faucet as it's coming out, is literally uh, bulging or piling up slightly in the direction toward the moon and the direction that's completely opposite of the moon. Okay. And the reason why it also goes to the direction opposite of the moon is because of the way centrifugal force works. So basically, you get one bulge for the moon, and then the other bulge occurs on the opposite side. Okay, which basically equates to the exact opposite side of Earth that's facing away from the moon. Okay, the areas in between, um, because you have all the water being bulged on the two sides, the areas between are experiencing low tides. So yeah, so the water piles up. One thing is that the sun also plays a minor role with gravitational attraction as well, and that's something that's typically not well known. So, so the sun can either work in tandem with the moon to create really high tides, or it can work against the moon, and that can cause basically no tides at all. Okay, we'll talk about that here in a minute. Okay, so when the moon and the sun are in direct alignment with each other, let me reword that. So when the moon, the sun, and Earth are all in direct alignment, okay, that means there's going to be a spring tide. Okay, and a spring tide is basically representative of being the once a month highest high tide and the once a month lowest low tide. Okay, and these occur during the new and full moon uh, times of the month. Okay, when the moon and the sun again are in direct alignment. Okay, so what you're getting is that adding of the gravitational attraction by both the moon and the sun added together to create that additional gravitational attraction causes the massive swings in the tides. Notice the bulges here and here, okay, bulges in water, and then on the opposite sides here and here, those would be the low tides. Now, neap tide. Okay, this is a time of the year which occurs during the first and third quarter moons, when the tide itself changes very little or over the course of the day, and that's because you have um, the basically the moon and the sun are at right angles to each other with the Earth in the middle. Okay, so the moon and the sun are essentially fighting each other with their individual attractions, and that's basically offsetting the effect of tides. So very little happens in the way of tides during neap tides. Okay. So that's a look at kind of the tides as associated with the astronomical side. We're going to revisit that. We're going to revisit tides very, pretty not shortly. We'll hit on it again when we look at astronomy later in the class. Uh, so let's move on here and look at some of the tidal patterns. Okay, so tides themselves. Okay, in addition to the gravitational attraction issue, tides are also affected by many different other variables, such like shape of the coastline, the topography of the local beach environment, stuff like that. So those also play a role as well. So it's not just gravitational attraction. Okay, but anyway, there are three different tidal patterns. There's diurnal, semi-diurnal, and mixed. Okay? So semi-diurnal tidal patterns, they have one single high tide and one single low tide each day. Okay, so these are as easy as you can get. Now, each of these tidal charts here, I want you to know, represents 2 days. So two 24-hour periods. Since you have one high tide, excuse me, rather 2 high tides, 2 high tides over 2 days, technically 2 low tides over 2 days as well. Okay. Yeah, I wish they would just do it for a 24-hour cycle. This kind of makes it confusing, but it is what it is. So one high tide, one low tide per day. Okay, this occurs along part of the Gulf of Mexico and the Mexican Yucatan coast as well. So, like I said, that's about the most basic tidal pattern you can get. Then there's the semi-diurnal tidal pattern. That's this red one here. Okay, this is where you have 2 high tides and 2 low tides each day, and the high tide and the low tide are of pretty much similar extent. So that means that the high tide is always going to be about the same elevation increase. Low tide is always going to be about the same elevation decrease. That same applies with diurnal down here as well. Okay. So basically, the semi-diurnal is just pretty much twice as many tides per day. That's really all it boils down to. Okay, so you expect to see that type of tidal pattern on the east coast of the U.S., okay, so the Atlantic coast. And then lastly is the more oddball one that occurs on the west coast of the U.S. It is called the mixed tidal pattern. Okay. And this one is quite interesting. So, like the diurnal, excuse me, like the semi-diurnal pattern, mixed pattern has 2 high tides and 2 low tides each day. But though each high tide and each low tide are not always of the same extent as in elevation wise, so they don't always, the tides aren't going to come up to the same elevation. Basically, they vary. Okay, and so that's why you're seeing this really odd setup here. So it's 2 high tides, 2 low tides per day, but they vary in height essentially, which makes it a little more challenging. So if you go out, to the West Coast, there are tidal pattern books, charts, I think they call them, tidal charts, that you can buy for really inexpensive, couple bucks. So if you're going to be recreating or boating at the coast on the West Coast, make sure you go get yourself a tidal chart before you go do that. Otherwise, you could find yourself in some pretty sticky situations with tides. Okay, a lot of people die that way out on the West Coast, unfortunately. So yeah, that's the kind of oddball one. All right. So yeah, I guess that's it for our presentation. Are there any questions on the tidal patterns or just anything in general that we looked at today? Okay. Not hearing anything. I'll take that as a no. So for next week, next Wednesday, we're going to switch gears and we're going to move to meteorology, rather. Okay. So we're going to start looking at the atmosphere and its behavior and structure. So make sure you read chapter 16 and 17 by next Wednesday. There are 2 videos from the Habitable Planet video series. And in the syllabus, there's the link, the URL for those specific videos. Okay. Just because it's a new video series, I put the actual link in there for you guys. Okay. So go ahead and watch that. That's it. Yeah. So anything else before we conclude for the week, rather? All right. Well, everybody have a good rest of your week. We'll see you next Wednesday.